Okay, class, welcome back. Today we're going to be talking about integration by substitution. Now this is going to be a tricky topic that's going to involve us, or it's going to require us to use some pattern recognition, basically just some general knowledge about math, and also use substitution. So the overall title of today's notes is Integration by Substitution. And we've got two objectives. One is to use pattern recognition to find an indefinite integral, and the other is basically just to give you the functions of what a composite function looks like. Okay. So now the entire subject of integration by substitution is based off of the chain rule and differentiation. If you remember the chain rule, as it's written out in math speak, and I'm going to push you guys. I want you guys to learn how to do this stuff because it's complex, it's challenging, and it is used all the time at all sorts of levels of mathematics. So the derivative of a function, remember we've got nested functions here. The derivative of nested functions is equal to the derivative of the outer function, leaving the inner function the same. In this case, my inner function is g of x, my outer function is capital F of x. So this is f prime. So the derivative of the outer function, leaving the inside the same, times the derivative of the inner function, g prime of x. Once again, this is the chain rule written out in math speak. Now, if I want to try to do a super quick integral of both sides of this function, say I integrated this d dx, right? And so this is the integral, this is the antiderivative, or sorry, this is the derivative, this is the antiderivative. Okay, so I'm just going to rewrite the same thing. Integrate both sides. I forgot my dx over here, dx. Okay, so if I take the integral, if I take the antiderivative of a derivative, they effectively cancel each other out. With a little bit of hand waving, it's pretty safe to say that f of g of x, right? So both of these calculus steps goes away. And I'm just left with f of g of x is going to be equal to this whole thing, the integral of f prime g of x times g prime of x dx. So this is basically the theorem that we're dealing with today. Okay? So if I have a function, if I give you a complex integral, right? Basically what you need to look for is an outside function, an inside function, and the derivative of the inside function. Okay? So I'm going to rewrite this one more time and make it a little bit more complete because I'm missing a few things. So let's give it one more time here. So in this case, in this case I'm using little f very purposely. So the integral of the function of a nested function times g prime of x dot dx is going to be equal to capital F. Remember, the capital F is a antiderivative of f. Capital F of g of x plus c. Of course, I forgot the plus c up here because there's always a constant anytime you do an indefinite integral. Now, I'm going to be using something that's called use substitution. And this is used all the time in calculus. Get used to it. And so if I just say u is equal to g of x, okay, this means that du dx, or I should say u prime, is equal to du dx, which is just going to be equal to g prime of x. Now I'm going to rearrange this, okay? So imagine I had du dx is equal to g prime of x, and I treat this dx as like a variable or a constant that I can move around. So if I multiply both sides by dx, right, this dx would cancel out, this dx would cancel out. What I end up with is du is equal to g prime of x dx. Now where am I going with this? I'll show exactly what I mean. So powered with this and powered with this, I can rewrite this function right here so that it makes a lot more sense and is quite a bit simpler. Okay, so let me just go ahead and do that. Let's rewrite that. Okay, so anywhere I see a g of x, I'm going to replace it with a u. And anywhere I see a g prime of x dx, I'm going to replace it with a du. So the same function I can rewrite as f, it's lowercase f, and now I've got a gx, so I'm going to replace it with a u, dot, and now I've got a g prime of x dx, which is right here, so I'm just going to say this is equal to du. And this is going to be equal to capital F of, and not g of x, once again, I'm replacing g of x with u, so capital F of u plus c. Simplifies things quite a bit. Makes it a little bit nicer to look at and quite a bit easier to think about. Now, the pattern part that I mentioned earlier, the thing that I really want to get you guys to be able to recognize is that when I write it here, when I write this function sort of the original terms, when I write the theorem in the original terms that I gave you, so with the g of x and the lowercase f and the g prime of x dx, this is going to be equal to capital F of g of x plus c. Okay, so now there's a couple things I want you to recognize. Just like when we were doing the chain rule with derivatives, there's the outer function and the inner function. So start being able to spot those. Okay, so right here we have an outside function. So before I was calling them nested functions. In this case, I'm calling it an outside function. And this thing right here, g of x, this is my inside function. So I've got an outside function, an inside function, and here I've got this, g prime of x, this is the derivative of my inside function. Derivative of inside function. Sorry, my n got a little carried away there. Now this might seem really obvious, but in the examples that I'm going to give you guys, I want you to be able to recognize that pattern. So we've got an outside function, and then the nested function, the one that's on the inside, is going to be here. And if you have the derivative of the function of the nested function there, you can solve the integral really, really easily. Okay? So let's jump into that with an example. So example the first. So I want you guys to recognize this. So we're trying to recognize this f of g of x times g prime of x pattern. So trying to get an idea of what this is. Now thankfully you guys have a thorough background in calculus. You can figure this out pretty quickly. And this one right here I'm making a little bit obvious as to what it is. Okay? So right away, if you recognize that, okay, I've got an outside function, an inside function, and a derivative of an inside function. Okay, so my outside function is going to be what? Let's take a second and just think about this. Okay, let's pause with the outside function actually, because it's easier to figure out what the inside function is right here. Okay, so this is inside some parentheses. This is going to be my inside function. And this is g of x. That's what I'm calling g of x. This, if I take the derivative of my inside function, right, constant goes away, I just end up with 2x. This is my g prime of x. That's the derivative of my inside function. That's nice. Now my outside function, once I have those two sort of peeled away, I recognize that, hey, my outside function is this squared term, right? So it's something squared. So outside. And this is f of x. So if I'm going to rewrite this, thinking about it in terms of that, right? So I know that g prime of x is going to be equal to 2x. And f of g of x is going to be equal to f. I know what my g of x is, x squared plus 1. So I'm just going to plug that in, x squared plus 1. Which is just going to be equal to, now my function is just whatever squared. Whatever's in here is squared. So my entire function is going to be x squared plus 1 squared. Because all my outer function is doing this, f is just squaring whatever I've got. Whatever I put in there is squaring. So once I know this, I can follow the power rule for integration and the theorem that we just wrote down. Okay, so basically, rewriting the original function, x squared plus 1 squared, 2x dx. Once again, this is going to be my f of x, or sorry, f of g of x, and this is going to be my g prime of x. All I need to do now is go back to the original function that I had. If we go back to our first page here. So that's going to be capital F of g of x plus c. Capital F of g of x plus c. So basically all I need to do is integrate this outer function right here, which is going to be giving me my capital F, and I can just ignore the g of x. So if I integrate this outer function right here, right? So I get this outer function, this is where I get x squared plus 1. So I'm leaving the g of x the same, and I'm basically just going 2 plus 1, pretending this whole thing is just an x, a variable by itself, divided by 2 plus 1, oops, 2 plus 1, plus c, which is just going to give me x squared plus 1 cubed. And there's a 1/3 that's going to coming from here, plus c. Now this is exactly what my answer is. This is 100% what the answer to this integration problem is. Now if I wanted to check my work really quickly, I could check it using the chain rule. So I need to take the derivative of this. So let's check it with the chain rule. Okay, so I take the derivative of my outer function. Once again, the constant drops away. So I have 1/3. The derivative of my outer function, so 3 goes in front. And then I leave the inner function the same, squared, right? So that drops down to a 2. 3 comes out front. Multiplied by the derivative of the inner function, which is just going to be 2x. Now my 3 and my 1/3 go away, and all I'm left with is x squared plus 1 squared times 2x. Now this is exactly what I started with. If I go all the way back up here, this is exactly what I started with right here. Beautiful. Okay, one more quick example. This one's using trigonometric functions, but don't worry. It's a nice and easy one. Okay, so say I want you guys to find the integral of 5 cosine of 5x dx. What would be my outer function? What would be my inner function? What would be the derivative of my inner function? Okay, so think about this for just a second. Okay, so my inner function, not too tough to figure out, right? So this is going to be 5x. It's going to be my g of x. Now my outer function right here is going to be the thing that's, so the cosine of 5x. So this is going to be my outer function, f of x. And the derivative of g of x, that's not too bad either. So the derivative of 5x is just going to be 5. So here I've got g prime of x. Not too bad. Now that I've got it set up, I can do the same exact process. Okay, so filling it in, so I can say, okay, the integral of 5 cosine of 5x dx is going to be equal to, since I know that 5 dx is going to be my g prime of x, I just need to fill it in, and I can say, okay, this is going to be equal to the antiderivative of the cosine of this function. So my 5x is going to stay the same. The g of x just goes along for the ride in this case, once I know what my g prime of x. And so the antiderivative of the cosine is just going to be the sine. So they've got the sine of 5x plus c. And this is my answer. Now the last thing I need to do, of course, is just to double check. So I'm taking the derivative of this. I need to take the chain rule. So I take the derivative of the outer function, in this case it's sine. So I could say d dx of the sine of 5x plus c. So the derivative of this function is going to be equal. So the derivative of the outer function is a cosine, leaving the inner function the same, multiplied by the derivative of the inner function times 5. And the plus c goes away, it just goes plus 0. And so just rewriting this, I get 5 cosine of 5x. So we're basically just doing the chain rule backwards. Now the trick is being able to recognize these patterns. We're going to work on this more in class tomorrow. I look forward to seeing you guys then. Make sure you're coming in with questions.